theoretical probability is what we're going to talk about now. And theoretical probability is all about, what should happen, not what actually happens, right? So you roll a die thousands of times. What should happen is each one of the numbers comes up 1 out of 6 times. Now, is that what's actually going to happen? Probably not. If you roll it enough times, will it eventually happen? Probably, assuming that the die is a fair die. So the mathematical or theoretical probability is based on what we theoretically expect to occur. You have 100 children, good Lord, first of all, find a hobby. Second of all, you should have about 50 boys and 50 girls, right? It is the chance of that event occurring in any trial of the experiment, what you would expect to happen, not what actually happens. In general, for an event A, and this is containing equally likely possible events, like I said, like a die, with 6 sides. If it's a fair die, all things should be equally likely. Then the probability that A occurs is the number of members of event A divided by the total number of outcomes. It looks complex, but it's really, really simple. Like I said, what's the probability of rolling a 1? 1 out of 6. Ta-da, just like that. Every probability should fall between 0 and 1 inclusive. 0 meaning impossible, cannot happen. 1 meaning guaranteed to happen. I roll a die. What's the probability I roll an even or an odd number?
0.5.
1. Guaranteed the number I roll will be even or odd. See how that works? I roll a standard 6-sided die. What's the probability my number is 0? 0. See, because it's impossible. All right. A ticket is randomly selected from a basket containing 3 green, 4 yellow, 5 blue tickets. And then it says determine the probability of getting some things. Okay, well, how many tickets is that? 12 tickets. Okay, well, 12 tickets. 12 tickets. So the first one says, what is the probability of pulling a green ticket? So I'm going to say probability of green is, well, there's 3 of them in there. So the probability that you pull a green one out is 3 out of 12, which does reduce to 1/4. You could call it 0.25 if you wanted to, or you could just leave it as a fraction. Let's just leave it as a fraction because, oh, no, you don't even have to reduce. IB doesn't care if you reduce or not. Isn't that nice? So you reach into this bag, and I say, now what's the probability that you pull out a green one or a yellow one? So he says 7 out of 12. How did you get the number 7?
I added green and yellow.
Oh, add green and yellow. That looks like a G. Let me fix my Y. So he says there are 3 green and 4 yellow out of the 12 possibilities, so 7/12. Oh, and so a minute ago, Bria asked if she needs to reduce her fractions. Strong word of advice. If it's a question with multiple parts, do not reduce, because there's a good chance that you're going to have to do some things with the other parts together. And if you don't reduce, they all have the same denominator, which makes life easy. Okay. Probability of an orange ticket.
Wait, why is your bank? 0. Oh, G1.
Yeah, 0. Yeah, there are no orange tickets in this hat, so there's a 0. There's a 0 out of 12 chance that that's going to happen. How about green, yellow, or blue? What?
Wait, why? 12.
Green or yellow or blue? 1. 12 out of 12. Looks like I wrote gory orb. Well, anyway, there's definitely a 1 out of 1, 12 out of 12 chance that you're going to pick a ticket out of this bag, basket, hat, whatever the heck we're pulling things out of right now. That's not too bad, right? Easy peasy? Yeah, good. An ordinary 6-sided die is rolled. Now we're going to determine the chance of these 4 things. Let's see, part A. What is the theoretical probability of rolling a 6? Yeah, it's 1 out of 6 because a die has 6 sides on it, and one of them has a 6 on it, so 1 out of 6. Well, if the probability of rolling a 6 is 1/6, what is the probability of not rolling a 6? Ah, good, 5/6. Because the probability that something happens plus the probability that something doesn't happen had better equal 1. The complement, we've already talked about that in 2 different lessons. And the probability of a 1 or a 2. 2/6, which reduces to a third, because we have 1 plus 1, because there's 1, 1 and 1, 2. Wow. Gives me 2/6, which reduces to 1/3. And again, if you're doing a multi-part question on a test, strong suggestion is do not reduce your fractions. There's a good chance that they're going to have to work together, and then they have common denominators. And D, if the probability of rolling a 1 or a 2 is 2/6, what's the probability of not rolling a 1 or a 2? Yeah. And you know what? How do you say not 1 or 2? Would be 4/6 or 2/3. Cool. So we're understanding how the complement works. That's great. Yes, Mark. Yeah, so the reason why I didn't use the prime symbol is because 6 wasn't a space. It wasn't a set. That's the only reason why I didn't say not 6. But yeah, that's why I was like, how would I want to say not 1 or 2? I was wanting to use prime symbols, but since 1 and 2 are not their own set, like if we described rolling a 1 or 2 as set alpha, then I could say the probability of alpha not or something weird like that, but now you're just going over and above just to be bougie. Okay. Look how fancy I am. Yay, two-dimensional grids. I love these things, he said sarcastically. Wait, what did Bria said? If you just pretend that you like it, maybe you will. All right, some two-dimensional grids. Let's do it. Use a two-dimensional grid to illustrate the sample space for tossing a coin and rolling a die at the exact same time. Okay, so let's do that first, and then we'll go ahead and answer questions A, B, or C. So here is our heads or tails for our coin, and down here will be our 1, 2, 3, 4, 5, or 6. Oh, I forgot to put my little tick marks for H and T. There we go. Much better.
I like how these look better.
Shucks. Ah, killing me. Kill me, Smalls. Killing me. That dumb left click selector thing is so sensitive. Gets on my nerves. Okay. There is all 12 possible outcomes. So for A, and we're not going to just jump straight to the answer, we're going to use the table here. For A, it says what's the probability of tossing a heads, and what that means is how many total times will a heads come up theoretically? 6, because there's 6 blue dots with a head out of 12, which, yeah, is a 1/2. Because the coin and the die don't care about what the other one rolled or flipped. They don't affect one another. Part B says the probability of a tails and a 5. So then what you do is you figure out all the places where we have a tails and a 5. There's only one of them. The only time that you get a tails and a 5 is right here. So that is 1 out of 12. See, I circled it, Gavin. It's the only time that a tails and a 5 can occur. Okay? Great. And then the last one, I'll stay on this side just so I'm not in the way of everybody. Now this one, it says getting a tails or a 5. So let's see, probability of tails or a 5. So it's not an and statement this time. This time, any time you saw a tails or a 5, you were happy. Bria, what'd you say? 7. And she said 7 because she probably saw this happening. Those 7 dots add up to 7 out of 12 because there are 6 opportunities of flipping a tails and there are 2 opportunities of rolling a 5, but we don't want to double count the 5. So 7 out of 12. That's not hard, is it? No, not hard at all. So I guess this is a good use for a two-dimensional grid. At least it really lays out all the options for you. Yes, Bria. I'm sorry, how do you what?
How do you know when to use the two-dimensional grid instead of the like H, T, and
Instead of a tree diagram? So the only time, I'll be honest with you, it doesn't matter. But the only time I would use a two-dimensional grid is when I was told to.
Okay.
That's just because I don't like drawing them. I would much rather have a tree diagram because the tree diagram has a better purpose, which you will see very, very soon. So because it works in a wider variety of situations, I just default to it. I only use the two-dimensional grid when I have to. Now for this one, to be honest with you, the two-dimensional grid was the easiest way to do this question. Would I have known that without doing the two-dimensional grid? No.
Is it easier to do like the tree diagram whenever there's like more y values?
The tree diagram is easier when things are not equally likely to occur. See, right now, because they're all equally likely, we can just say, okay, this thing works great. But when things are not equally likely, which is more often than not, the tree diagram is more handy. And you will see that very, very, very soon. This one asks me to display the possible results when two dice are rolled and the scores are added together. This is kind of like a two-dimensional grid, but instead of just putting the dots, I'm going to be putting the scores. Anybody ever play Settlers of Catan? Vaguely. I didn't say do you remember it. I said did you play it? Okay. Settlers of Catan. In the Settlers of Catan, you roll 2 die for every time it's your turn. It's a very fun game. And the score, that the sum of the die does things in the game. So the sum of the die is very, very important to you. Let's see. So let's just add these up. 2, 3, 4, 5, 6, 7. 3, 4, 5, 6, 7, 8. 4, 5, 6, 7, 8.
How come you went to 7? Oh, the sum is 7.
Because the die only has 6 sides on it. This guy. All right.
Well, I was confused because I just saw 7.
Because you didn't read the question? Gifted student? Okay. Those are the sums that are possible when you roll 2 die. It says find the probability that the sum of the dice is 7. Well, how many different outcomes are up there? If it was a two-dimensional grid, how many outcomes would there have been? No.
36.
How many? 36, thank you. I said how many possible outcomes are there? There are 36 possible outcomes if it was a two-dimensional grid. But how many of them add up to 7? Well, let's see. Yikes, that was way too big. I'm seeing 1, 2, 3, 4, 5. Bingo! 6 of them add up to the sum of 7. So the probability of getting a sum of 7 is 6 out of 36 times, which is 1 out of 6 times. So why was I talking about the Settlers of Catan? Because in the Settlers of Catan, every time a 7 is rolled, bad things happen. The Marauder or something like that takes half your crap. And then he gets to move to someone else's space and block their stuff. But why does it happen when the 7 is rolled? It's the real question.
Because 7 has the highest probability.
Because 7 has the highest probability of being rolled when you roll 2 die. It's the most common sum when you roll 2 die. And if you've ever played the Settlers of Catan, you'll know that the 6s and the 8s are red. That's because they're the second most common sums. Behind the 7, 6 and 8 is the second most common. So when you're playing that game, you want to occupy spaces with 6s or 8s. Neat, huh? The Settlers of Catan is amazing. It's fantastic. And it has expansions for 5 to 6 players. It has like 3 or 4 different versions of the game. There's the Seafarers edition. There's there's one that's like Cities and Castles edition. And they just came out with a new edition too. It's incredible.
Can we play it?
Nope.
Okay.
This Venn diagram represents the set of all children in a class. You guys, I guess. Each dot represents a student. The event E, as you can see up there, is the green circle. The event E shows all of the students that have blue eyes. This is a very Aryan classroom. Determine the probability that a randomly selected child, A has blue eyes, B does not have blue eyes. Well, you need to know how many. No, it's 1/6. 6 over 36 is 1/6.
Yeah.
Yeah?
That was over 30. Why?
No,
Because that's what you put.
no, I didn't. I put 36. That's a 6.
That looks like a 0.
That doesn't look anything like a 0.
Are you blind?
Maybe if you're high.
Okay.
No, it's okay.
That's stupid.
Hey, what if he's all 3?
You're right.
Okay, so what we need to know is how many people are in this classroom. I'm seeing 1, 2, 3, 4, 5, 6, 7, 8, and 12, 13, 14, 15. Looks like 23 dots to me. Looks like 23.
No, it's
Yes, it does. Okay, so what is the probability of blue eyes? Well, looks like 1, 2, 3, 4, 5, 6, 7, 8 out of 23.
that hurts my eyes.
Wow, this was a difficult question. So there's A. How about B? Probability of not blue.
Oh my god.
Well, if 8 out of 23 is blue, then the other 15 out of 23 is not blue. You know what? Let's do better notes than that. Let's do this. Let's show me using the complement. Yes, because this is a really important idea, and it makes a lot of stuff easier to do. Rather than just have the answer, let's show why it's the answer. That's why it's the answer.
Because 13 over 23 is about blue.
And I think we're on to our last example. Look, theoretical probability is easy, especially when all things are equally likely. Especially when all things are equally likely. Is this the last one? Yes, it is. In a class of 30 students,
Oh my god.
19 students study physics, 17 study chemistry, 15 study both. Display this information in a Venn diagram. This exact question was on your homework?
Maybe the numbers are different, but
The numbers are different, yeah. Unless it's the exact question, I don't know. Let's Venn diagram this bad boy.
Venn diagram.
What do we have? Physics and chemistry? Physics and chemistry. Cool. 30 students study physics, 17 study chemistry, 15 study both. Okay, well, if there's a 15 here and physics adds up to 19, then the physics only circle or physics only crescent should be 19 minus 15, 4. And if the chemistry circle has 17 students in it, but 15 of them are in the middle, then the chemistry crescent would be 17 minus 15, or 2. That only adds up to 21. That's 21 students.
That means,
How many?
none.
There are 9 people that study neither. There. Now we've accounted for all 30 of our students. Part A. What is the probability? Probability a randomly selected class member studies both subjects.
What happened?
Rather than reducing first, we're going to say 15 over 30, which reduces to 1/2. And remember, it is often useful to not reduce your fractions when you're doing probabilities when there are multiple parts. Just going to keep saying that. Part B. The probability of at least one subject. And you know what? Instead of writing at least one, I'm going to say greater than or equal to 1. That's just better. And basically, that would be as long as you didn't grab one of those 9 people, you can either add up the 4, the 15, and the 2 and say 21 out of 30, or you could say 1 minus 9 out of 30. Either way, you're going to get 21 out of 30. I'm going to say 1 minus 9 out of 30. And here's why. Here's why. often it is easier to figure out the probability that something doesn't happen and just subtract it from 1 than it is to figure out the probability that something does happen. That's difficult a lot of times. So this is a very valuable skill of using the complement to work around a question. C, so we're looking for physics but not chemistry. So that the words for this is physics only. So probability of physics only.
Wait,
What?
never mind.
Okay.
Sorry.
No, you're fine. So probability of physics only, how many students is that?
4.
4 out of 30, which does reduce to 2 out of 15, but you don't have to. It's not necessary. D. It says exactly 1 subject. Probability of exactly 1. That's not the same as at least 1.
That's only like 1.
So how many people study exactly 1?
That's
6, because that's the 4, and the notes want me to do it like this. Oh, there's these 4, and then there's these 2 out of 30, which is 6 out of 30. And this time it is 6 out of 30, which reduces to 1/5. And then lastly, I'm just making myself some more space. Also, my people in the cheap seats, it's hard for them to see when I write that low. It wants to know the probability of pulling someone that studies neither subject. So that means none. So E, probability of none, would give me how many? There are 9 of those people. That reduces to 3/10. So your lesson on theoretical probability is complete, and it is easy. You're welcome.